Hello everyone, my name is A. Ritika Reddy, working as an assistant professor in Vignyan's Institute of Information and Technology. In today's session, you will be seeing some more topics related to discrete mathematical structures. You will be seeing these contents in this session. Firstly, it contains the algebraic structures. Nextly, you will be learning what are semigroups and what are monoids, followed by what is homomorphism and what is homomorphism between semigroups and monoids, followed by what are groups and subgroups. Next, you will be learning about the abelian groups. Okay. Firstly, before going into all these contents, firstly we need to learn what is a binary operation exactly it is. When coming to the definition, a binary operation is an operation that combines two elements to produce another element. Binary, what is this term binary? What is bi? Binary means two terms. So, combination of two terms using some operator is called as the binary operation. So, you are performing the binary operation with, suppose these are the two terms A and B, and if you want to perform the binary operation between these two terms, then this is the place where you need to place the operator. If you place plus over here, then you are adding these two terms and the byproduct will be obtained as the result. Similarly, in the place of plus, you can keep multiplication, division or integer or modulus or anything, whatever you want. So, binary operation is nothing but combination of two operands by means of some operator. And coming to the symbolic notation, a binary operation on non-empty set A is a mapping function between A cross A. What is this A cross A? It is nothing but the Cartesian products. Through Cartesian product you will be getting the ordered pair, right? So, you are combining different combinations of the ordered pairs in order to get the third result, and you need to combine such a way that this function f is defined on every pair of elements in A. If you are denoting in this way, then this means that you are defining this function on each and every element of the set A. This is the first rule. Coming to the second one, f uniquely associates each pair of elements in A to some elements of E. For suppose here A contains some 1, 2, 3, and if you want to do the binary operation, then you need to combine each and every element uniquely. That means you need to combine 1, 2, next 2, 3, 1, 3 in that way. Okay. Next, as I said earlier, binary operation you can perform on division, multiplication, addition, subtraction. This is about the basics of binary operations. Next, algebraic structures. What is this algebraic structures? A non-empty set S is called as an algebraic structure with respect to binary operator if it follows the below axiom. What is this axiom? It should obey the closure property. That means if set A contains 1, 2, 3, 6, suppose, and you are performing the binary operation between 2, 3, and the binary operator here I am giving you is the multiplication. So, if you multiply with this 2 into 3, then what is the result you are getting? 6. So, if you are saying this A is an algebraic structure, then as 6 as whatever result which is obtained by 2 into 3 is contained in 6, then it is obeying the closure property. So, this set is obeying under algebraic structure. So, if a set of elements obeys the closure property, then it is said to be in algebraic structure. That itself I have written over here. Okay, this is one more example, guys. Here a set S contains 1, minus 1, and I am saying it is algebraic structure under star. So, the binary operator over here is the multiplication. That means 1 star 1. What you will be getting? 1. Is 1 present in this? Yes. 1 star minus 1. What you will be getting? Minus 1. Is minus 1 present? Yes. Next I will be doing minus 1 star minus 1. Minus 1 into minus 1, what I will be getting? 1. Is it present? Yes. Next I will be doing minus 1 star plus 1. What I will be getting? Minus 1. Is minus 1 present? Yes. It is present in this. So, this S is equal to 1, minus 1 is closed under the multiplication, and another result having plus and minus as the binary operators, then in that case it is not closed under plus and minus. You take it as an example. Try to add this and subtract these elements. Then you will be getting the elements that are present outside the set S. So, this set is not closed under plus addition and subtraction. Okay, this is about the algebraic structures. Next, what are semi-groups? It is a non-empty set S is called a semi-group. It follows the below axioms. What are those axioms? First one is the closure. What is the closure? I have already said to you. Next is the associative. What is associative? You need to interchange the braces. That means whatever result you are getting by the in this way in the left hand side, if you interchange the braces, in that case also you need to get the same result. So, in that case it is said to be obeying associative. So, if a set S, I am given a set S and I am asked to show whether it is a semi-group or not, then in that case I need to show whether it is following the closure property under some given set operator, binary operator, and whether it is obeying the associative rule or not. See, this is the example. A set of positive integers excluding 0 with an addition operator is a semi-group. So, the binary operator which is mentioned over here, addition, is a semi-group. Is it true or not? 1 plus 1, what you are getting? 3. 3 plus 5, what are you getting? 8. All these elements are present inside the set itself. So, it is obeying the closure under addition. Okay? And what about the associative? In this given set, if you do 2 plus 3 plus 4 and you will be doing 2 plus 3 plus 4. Here you have interchanged the braces. Are you getting the same result if you interchange the braces? Yes. Here also you will be getting 9 and here also you will be getting 9. So, LHS is equal to RHS. So, it is obeying the associative rule. So, a semi-group is nothing but which obeys the closure property under certain binary operation and it obeys the associative rule also. Next. The other one is the monoids. So, in similar way like the algebraic structures and the semi-group, it also need to obey certain axioms in order to follow this. The first one is the closure, the second one is the associative, and the third one is the identity element. What is this identity element? If you suppose E is an identity element, if you multiply this identity elements with our given set element, then you will be getting result A. Similarly, here if you multiply our set element with identity element, here also you will be getting A. Then in that case, it is obeying the identity law property. See, this is the example. Same example I have taken, but here I have taken the multiplication property because for identity element, they should be multiplied with each other in order to get the given result. Take it as an assignment. As I already said, closure and associative is obeyed on this. Similarly, for the identity also will be obeyed. Okay, the next one is groups. So, if you see the definition, a non-empty set G is called a group if it follows the following axioms. What are those axioms? Closure, associativity, identity and inverse. Okay, you have learned about closure, associativity, identity until the previous one. What is the extra one which is adding over here? The inverse property. You will be knowing that means it should be following all these 4 properties. Whatever given set is there, if it follows all these 4 properties, then in that case it is said to be a group. I am given a set Z plus. What is a Z? Z means a set of integers. And what is the binary operation which I have mentioned over there? Addition. So, on this set of integers, if a binary operator is asked to obey all these 4 conditions, then it is said to be a group. How it is asked? Let me verify. Z. How this Z can be written? 1, 2, 3 and so on, and the negative numbers can also be included. Coming to the closure property. What is this closure property? 1 plus 2. What I am getting? 3. Is 3 present in group? Yes. Next. 4 plus 5. What I am getting? 9. Is 9 present? Yes. So, it is, you can check them randomly. So, it is obeying the closure property. Coming to the associative property. Associative property over the addition of elements. That means, you will be doing 2 plus 3 plus 4 and you will be doing 2 plus 3 plus 4. What is the result you will be getting? Here you will be getting 9 and here also you will be getting 9. So LHS you are getting equal to the RHS. So it is obeying the associative property also. Next comes the identity element. What is this identity property? A star E equal to E star A is equal to A. So if you apply the addition operation like 2 plus 1 is equal to 1 plus 2, what you will be getting? 3. Or you will be adding 5 plus 1 plus 1 plus 5, what you will be getting? 6. Are these elements present in the set G itself, given set itself? Yes. So it is obeying the identity element property also. Next comes the inverse condition. What is the inverse? If you are given 2, what is the inverse? 1 by 2. So if you are asked to obey the binary operator addition, so 2 plus 1 by 2, what you will be getting? 1 by 2 plus 2. What you will be getting as the final result? 5 by 2. In both cases, you are getting same 5 by 2, then it is obeying the inverse property also. Similarly, over matrix multiplication also you can apply the closure, associativity, identity and inverse operation and you can check. Next comes the abelian group. It is very much similar, but the extra axiom which is adding over here is the commutative property. What is this commutative property? A star B, whatever result you will be getting, that will be equal to B star A. So I am given a set G and I am asked to obey the addition property over this. So is it obeying the closure property? Yes, it is obeying, because whatever elements you add inside the set of elements will be present inside the set G itself. Yes, it is adding. Next, associative 2 plus 3 plus 4, whatever you will be doing are present inside this group itself. So associativity is also obeying. Next, identity element. If you add an element with an identity operator like 3 plus 1 or 1 plus 3, in both cases you will be getting 4 only. So and this 4 is present in this group itself. So it is obeying the identity element property also. Next, inverse. As I already said, our 1 by 2 plus 2 plus 2 plus 1 by 2, whatever thing you will be getting, same result you will be obtaining over here. So that is also present in our given group itself. And next comes the commutative property. What is this commutative property? 2 plus 3 will be definitely equal to 3 plus 2 and the both result will be equal to 5. Is this 5 present over here? Yes, it is present. So it is obeying the commutative property also. Okay. So identity element, is it obeying identity law property? Yes, it is obeying the identity law property also with respect to these set of elements. What is the other one? Inverse. Is it obeying inverse element? You just try whether our set of elements with in combination with the binary operator addition with the inverse of those elements, are they giving the same result or not? Yes, in that case also it will be obeying. Next comes the commutative law. Commutative law also is very easy. 2 plus 3 will be equal to, definitely equal to 3 plus 2. So it is obeying all the elements of all these things. Okay. So this set comes under the abelian group. Next is the subgroup. Subgroup. What is a subgroup? You have already listened, right, about subset. What is a set? A set is nothing but a well-defined collection of objects. What is a subset? It is also a well-defined collection of objects, but it contains only part of elements. Similarly, a subgroup is also similar to group, but it contains lesser number of elements when compared to the group. A subgroup H is a subset of group denoted by H less than or equal to G if it satisfies the 4 property. What are these 4 properties? These 4 properties are nothing but the properties of our group. So a subgroup is nothing but a group, but the condition is that it should be less than or equal to the group, but not greater than the group. And you have already learned about the proper subset, right? As I already said, what is a proper subset? If it contains at least one element that doesn't contain in the set, then it is called as the proper subset. Similarly, here also a subgroup H of group G that does not include the whole group G is called as the proper subgroup. If it does not include at least some elements of that group G, then in that case it is called as the proper subgroup. Here less than or equal to condition is there, right? Here equal to condition is obeyed. So always the elements of this proper subgroup should be less than the group. And this is the, and see, this is the example of the subgroup. Here I am taken the group elements like 1, I, minus 1, minus I. And I have taken the elements H1 is equal to 1. Is it a subgroup? Yes. Is it H2 is equal to 1 comma minus 1? Is it subgroup? Yes, because 1 comma minus 1 is present in the group G. I am taken H3. It contains what elements? 2 comma I. Is 2 comma I a member of the subgroup? No, because it contains the element which is not present in group G. Okay, this is about the subgroup. This is very much similar to our subset concept, but the terminology is varied. Next, okay, coming to the summary, in today's session you have learned what are binary operations, followed by the algebraic structures, followed by the semi-groups, followed by what are monoids, followed by what are abelian groups, and followed by what are the subgroups. Okay, thank you.